Okay, now it's streaming. So strange. Okay, Twitch is working. Let's check YouTube. Okay, YouTube is working as well. Okay, let's get started. Yesterday I was using Visual Studio Code, not code, just Visual Studio Community, and it was very annoying to use. So I have now changed to using CLion. I downloaded it, I set everything up, figure out how the CMake thing works, and now it runs. There we go. This is just a simple window, what we were working on yesterday. And if anyone else wants, they can just like copy the CMake code and set things up for the CLion as well. Okay. Now we're back here. I've also changed the camera position uh, so that it doesn't block all the text anymore. Now it's kind of custom. If it's a game engine, it'll be on the left. If it's a text editor or something, it'll be on the right. Depends on where all the important things in the program are. I had to configure that manually. So let's get started.
So how does a computer draw? Well, we can break down the difficult problem of trying to have a computer draw anything into just having it draw a series of triangles, and being pipeline in Vulkan solves for us. The graphics pipeline is a linear sequence of stages, where each stage takes as input some data, performs some operations on it, and outputs the transformed data as input into the next stage. We can think of our graphics pipeline like a factory assembly line, and at each stage our raw data is refined into something closer to resembling our final image. The first stage is the input assembler, which takes as input a list of numbers and groups them together into geometry. For our triangle example, the first 6 numbers may be used to form the first triangle, and the next 6 a second triangle, and so on. Next, the vertex shader processes each vertex individually and performs transformations such as rotations and
not showing tessellation or geometry stages. I guess that's too complicated for this, but input vertex shader, rasterization, fragment shader, color blending.
translations. The rasterization stage
like
breaks up our geometry into fragments
so.
for each pixel our triangle overlaps. The fragment shader processes each fragment individually and outputs values such as the color by using interpolated data from things like textures, normals, and lighting. And finally, the color blending stage applies operations to mix the values from multiple fragments that correspond to the same pixel in the final image. This is a simplified overview of the graphics pipeline, and don't worry if you're having trouble understanding what each stage does right now, as we'll go into much more detail in the coming tutorials. This is just to give you a high-level overview of how things work so that you're able to keep the bigger picture in mind. As programmers, we have less control over what operations these stages perform. We can configure each stage by setting variables that modify the stage's behavior. For the programmable stages, we have the ability to upload our own code to be executed by the GPU. These little programs.
Okay, so this will modify the like 3D mesh. This, I guess, modifies the pixels.
That live on the GPU are called shaders and can be written in a C-like language called GLSL. In this video, we will code a basic vertex and fragment shader to draw our first triangle. Note that in this diagram, I am not showing the tessellation or geometry shader stages. These stages are programmable and occur between the vertex shader and the rasterization stage, but for our purposes, we do not need to use this functionality anytime soon. Now, one thing you may be wondering is why is all of this necessary? Wouldn't it be simpler to code a program in C++ that draws a triangle for us? And you'd be right, it would be simpler, but it would be much, much slower. What GPUs are specifically made for is doing parallel computing. So unlike a CPU, which would have to process one vertex at a time, modern GPUs are capable of processing thousands of vertices concurrently. Even
like the south style of this graph.
top-of-the-line multi-core CPUs cannot come close to that processing power. But for all this power, there's a trade-off. When programming for GPUs, we are much more limited in what we can do, and we can't write code different. And that's our first vertex shader and fragment shader.
Okay. Then first app, HVPP. Yeah.
Create a folder called shaders, and in this folder, add a file simple_shader.vert.
So Is it loading for this? Let's see, directory, shadows, new file, simple shadow, not watch. Install plugins. Let's see. What plugin is that for this? Oh, let's get the support. There are two different programs. Which one has been updated more recently? Additional info. Say non-trader, non-trader. Trigger. Code completion refactor formatter. This is just GLSL. Let's get this one, I guess. Should we get both? Okay, I have to restart. It's restarted now.
The first thing we need to do is specify which version of
File button. Yeah,
using.
just
We do this with hashtag version 4.5. Next, we need a main
hashtag version. Word name. That's also a sample position. Back to lessons. Back to let's set it up. Back to reference 0.5 minus 0.5, 0.5. Minus 0.5, 0.5. Okay.
this. Hard-coding your values in a vertex shader isn't something you typically do. Usually we pass in our values using a vertex buffer, but for now, it's all right. Finally, let's assign GL position a value. It's a vector.
Positions. Square bracket GL vertex. Can I not reuse this?
The third component is the Z value, which ranges from
Is it 0, let's see. New formats. Code, CLion. All spaces in between. How do I get this to be automatic? Say code cleaner, code style. If I do reformat, okay, there should be an option to format on save. Reformat code, reformat file. Let's check the settings. Format on save. Actions on save. Reformat, optimize, rearrange, and code cleanup. Okay, so now and do this and save. Okay, format it. Great. Yeah, now it's
for our
making a
fragment
flag
shader.
shader.
Same as before, we start with hashtag version.
Say flag. Always name it manually. Simple shadow dot flag.
So we need to declare it ourselves.
National version 450. Void in. Layout. Caching. Let's disable the GLSL support plugin and just the normal GLSL. That's loading. Today I want to at least get through 2 of these tutorials.
With each component being the red, green, blue, and
Out color. Yeah, this will basically be a red color. RGB alpha.
we need to compile our shader code into an intermediate binary format known as Standard Portable Intermediate Representation 5. You've actually already downloaded this compiler when you downloaded the Vulkan SDK. How you will do this will differ based on if you're working on Windows, Linux, or Mac. For Mac OS and Linux, navigate to where you installed the Vulkan SDK and locate the file glslc and copy the file path to this program. For Linux, it will likely be in the subdirectory of Vulkan, version number /x8664/bin directory.
What is this?
Before being executed, we need to fragment shader runs on a per fragment basis, which are determined by what pixels our geometry mostly contains during the rasterization stage. Similar to how C++ code needs to be compiled before being executed, we need to compile our shader code into an intermediate binary format known as Standard Portable Intermediate Representation 5. You've actually already downloaded this compiler when you downloaded the Vulkan SDK. How you will do this will differ based on if you're working on Windows, Linux, or Mac. For Mac OS and Linux, navigate to where you installed the Vulkan SDK and locate the file glslc and copy the file path to this program. For Linux, it will likely be in the subdirectory of Vulkan, version number /x8664 macOS/bin folder compiler. Create a new bash scripting file, compile.sh, in your main directory. Then paste the path you just copied. Make sure you have glslc at the end of your path. The first argument is the file path to our shader, so shaders/symbol_shader.vert. Then -o to specify our compiled output file's name. In this case, we use the same name, and then add .spv file extension at the end. As your compiler working is to install it separately using installed the Vulkan SDK. Windows, open File Explorer and navigate to the directory you installed the Vulkan SDK. Then open the folder for your version number, then bin32 and locate the glslc file. If you hold Shift and right-click, you should see an option to copy as path. Once you have the file path copied, create a new file, compile.bat in your.
Okay, let's create a new file. New file. Compile. No, that. Let's see what plugins are there first. Okay, they're all kind of like unofficial support. Reviews. That range isn't verified. Reviews. Cancel.
Then paste the path you just copied.
Oh, let's save. Let me quickly find the folder. File Explorer. Can you see? Where was it saved? Say K, maybe under this program files. Vulkan, video line Vulkan RT. No. Maybe under program files x86. VB, resume Vulkan here. Let me open up Visual Studio and check that. Visual Studio. Why did I even save this SDK here? So Vulkan. Yeah, Vulkan Cube, open file location. Open file location again. Yeah, I think I found it. Okay, let's say 1.10.32. Okay, I just have normal pen. Now GL SL. Okay, found it. Copy as path. Yeah.
The quotations. The first argument is the file path to our shader. So
Okay, shaders backslash. Yeah. Yeah.
in this case, use the same name and add the .spv file extension. Then copy this entire line and change the .virt file extension to .frag.
Let's put underscore word and underscore file.
File Explorer, double-click your compile.bat file. In your shader
Okay, and pause.
folder, you should now see two more files with the .spv extensions. This is our final line, so we will be able to view the output after running. In case, use the same name and add the .spv file extension. Then copy this line and change the .virt file extension to .frag. Then add pause as the final line, so we will be able to view the output after running. Save this file, and then in your File Explorer, double-click your compile.bat file. In your shader folder, you should now see two more.
Okay, let's see. Okay, making Vulkan. Let's open this. Okay, got made.
Files with the .spv extensions. This is our compiled shader code. So now that we have the header.
Okay, let's see. Create new C++ header file. LVE pipeline. Okay. Okay, it doesn't need to be added here. Automatically gets added. Okay.
In your namespace.
Shell tag namespace LVE plus LVE pipeline. hash include string.
Next,
Now let's see public we weapon const std string and what file path const std string ampersand flag file. Okay.
two private functions. The first is going to be a static function that returns a vector of characters called readFile, and this is going to take a const string ref to a file path, like in our constructors. We also need to include vector.
Let's add this hash include vector private no start. Okay, it automatically resets itself.
Then our second function is going
Static std vector cover read file points. Yeah, that's clear. Let me just check one thing. Yeah, audio split.
all right. Now let's add
Void create graphics pipeline constant word file path constant flag file path. What is the std library called? C++ std library used to be called like stdio.h or something like that, right? Standard library X functions from Livestream, Livestream, new string, array deq, set vector, any. Also, do a thing called like std. C stdi. Yeah. Close printf, freed, clear. I just leave it. Standard library header, float, open, f close, outputs gets printf. No, not what I'm looking for. What I
Add an implementation for our pipeline. Add a new file lve_pipeline.cpp.
Okay, new file, new C++ class, LVE pipeline. Add target now.
Include our pipeline header and
Include the pipeline. Let's see. Headers. Okay, they're just doing direct. Right. Okay, this can be closed. Okay, this is showing as HTTP. Rename Shift 6. See. First up, .http. Let's build a scene. Okay, cool. Yeah, right. Yeah, this one can be deleted. Okay, let's rebuild just in case. Okay, not showing any squiggly lines anymore. Visual Studio, I don't think it would have done half of these things properly. So it's nice that I've switched. Name space away. Then std vector large. Let me just close these other things. This doesn't have to be the main CPP window. I'll open it if it's required. Yeah, there you go.
Okay, so to read our shader files, we're going to use an input file stream object.
Okay, LVE pipeline, read file path. Okay.
The standard library include fstream.
No return statement, no function returning non-void.
Then let's
load stream.
new input file stream variable. So std if stream file, then put your file path as the first argument, and as the second argument, we are going to put some bit flags. The first bit flag 8.
Yeah. Std if stream. File path. iOS 8, iOS binary.
Open, we seek to the end immediately. This makes getting the size a bit more convenient, and we read it in as a binary to avoid any unwanted text transformations from occurring. Next, let's check that the file was successfully opened. So if not file.isOpen, then in this case, if we failed to open the file, we'll just throw an error. Include std except.
Must include std except. If file is open,
Failed to open file plus file path. If you're getting this error, it's most likely because your file path is incorrect,
so failed to open file plus file.
to open that file. So now we need the size of the file. So size t file, size equals static cast size t file.telg. So because of the 8-bit flag, we're already at the end of the file. So when we use telg, we get the last position, which is the file size. Next, create a vector of characters.
Size t file size telg.
This is our character buffer, and we're going to initialize with the size of the file. The next thing is to seek to the start of the
Steady vector or buffer file size file cg file.buffer file size. File.close. Let's see, return buffer. Let's see what's the error. Narrowing conversion from size t to sign type stream size as implementation defined. See. Okay, it doesn't
to be our read file function. Next, let's implement our create graphics pipeline. Similarly, let's go back to our header and grab our create graphics pipeline function signature. Add your class name
void LV pipeline create graphics.
So now inside this function, all we're going to do is read in our vertex and fragment code. We're not going to
Here, let's Livestream include Livestream.
now the last function to
There's definitely something for
constructor. Go back
this STD thing.
to our header to grab our function signature and paste it.
I'll check it out after the stream.
Add LVE pipeline, and all this is going to do is call our create graphics pipeline helper function. Back to our header to grab our function signature and paste it. Add LVE pipeline, and all this is going to do is call our create graphics pipeline helper function. And do the same.
Okay, let's do this. STD out, printing the size, and I'll say out. Yeah.
And I need to also include IO stream. Now the last function to implement is our constructor. Go back to our header. Now the last function to implement is our constructor. Go back to our header.
So
To grab our function signature and paste it. All this is going to do is call our create graphics pipeline helper function. And
copy paste. Is this like named differently or something?
parameters. Now finally, let's instantiate an
create graphics out file path flag file path.
LVE pipeline. So back in our first app header under window, well, first include LVE pipeline.hpp. Then
Hashtag and HPP. Dash include LV pipeline.hpp.
LVE pipeline, and pass the file.
LV pipeline. LV pipeline. Shadows, simple
Extension to frag. So a common mistake. Don't forget we want to read in our compiled code, not our original code. So make sure to add the .spv file.
.spv. Now this will go after rename them. match.
Extension to the file paths. So save and compile. And in our console, we can see vertex shader code size 1164 characters, which sounds
Let's build. Let's run it. Not cancel itself in the terminal. Let's say might have to rename these. But and where's the start? Dot flag. Delete. Let's see, open and file explorer. Open and explore. Yeah. Let's run it. Okay. Let's see. Still getting any errors. Fail to open file. Is there any spelling mistake somewhere? Some shadow. Shadow is. Okay, that function can be made private. Const.
and fragment shader code size 424 characters. Perfect.
OV pipeline.
Okay, so I
Okay, is there something in this?
directory, you installed the Vulkan SDK. Then open the folder for your version number, then bin32 and locate the glslc file. If you hold shift and right click, you should see an option to copy as path. Once you have the file path copied, create a new file, compile.bat in your main directory. Then paste the path you just copied and remove the quotations. The first argument is the executed. We need to compile
100. Let's see. Out color 4.
our shader code into an intermediate binary format known as Standard Portable Intermediate Representation 5.
Am I missing something here? Can we make static?
Actually already downloaded this compiler when you downloaded the Vulkan SDK. How you will do this will differ based on if you're working with LC, and copy bin in folder. Copy a folder for your version number in your main directory. Create a new file.
Okay. The vote is looking correct.
File.bat in your main directory. Then paste the path you just copied and remove the quotations. The first argument is the file path to our shader. So shaders / simple_shader.bert. Then -o to specify our compiled outputs file name. In this case, use the same name and add the line so we will be able to view the
.flag.spv.
after running. Save this file, and then in your File Explorer, double-click your compile.bat file. In your shader folder, you should now see 2 more files with the .spv extensions. This is our compiled shader code. So now that we have compiled shader code, we need to read these files into our program. We're going to start by creating a new header file, lve_pipeline.hpp. Add a header.
Constant.
Because we'll have a second. So the first is going to be a static function that returns a vector of characters called readFile. And this is going to
Static string for both.
we also need to include vector. And then our second function is going to be a helper function, void create graphics pipeline. And it's going to take the exact same arguments as our constructor.
Constant flag for both.
All right, now let's add an implementation for our pipeline. Add a new file. _pipeline.cpp. Include our pipeline header and add your namespace. Now, in your header file, grab the read file function signature and paste that in. Remove static and add your class name before your function name.
Okay. What is this one?
Okay, so to read our shader files, we're going to use an input file stream object. So from the standard library, include fstream. Then let's initialize a new input file stream variable. So std if stream file, then put your file path as the first argument, and as the second argument, we are going to put some bit flags. std ios 8 and std ios binary. The first
Okay, we've gone through this. This is here.
first bit flag 8 means that when the file is open, we seek to the end immediately. This makes getting the size a bit more convenient. And we read it in as a binary to avoid any unwanted text transformations from occurring. Next, let's check that the file was successfully opened. So if
std binary, std 8.
not file.is file path. Now we need the size of the file. So size t file size equals static cast size t file.telg. So because of the 8-bit flag, we're already at the end of the file. So when we use telg, we get the last position, which is the file size. Next, create a vector of characters. This is our character buffer, and we're going to initialize with the size of the file. The next thing is to seek to the start of
Okay, buffer size. Static size table.
Because now we actually want to read the data. And to read this data into our buffer.data, and the number of bytes we read is equal to file size. Now close your file with file.close and return your buffer.
Okay, so far everything is matching.
So that's going to be our read file function. Next, let's implement our create graphics pipeline. Similarly, let's go back to our header and grab our create graphics pipeline function signature. Add your class name. So now inside this function, all we're going to do is read in our vertex and fragment
Node file path, frag file path, read.
We're not going to do anything with it until the next tutorial, but just to make sure our read file function is working correctly, let's output the size of our vertex shader code to our console. Duplicate this line and do the same for fragment shader.
Okay, everything seems to be fine here.
Duplicate this line and do the same for fragment shader. And I need to also include IO stream. Now the last function to implement is our constructor. Go back to our header to grab our function signature and paste it. Add LVE pipeline, and all this is going to do is call our create graphics pipeline helper function and pass through our parameters. Now finally, let's first include LVE pipeline.hpp. Then under window, LVE pipeline, and pass the file paths to our vertex and fragment shaders. So this file path is relative to wherever our execute.
Semicolon, namespace LVE.
Shader / simple _ shader.vert. And we can copy this and change the file extension to frag.
Let's compile. Build. Yeah, I guess I didn't build that.
Code size 1164 characters, which sounds about right.
What is exit code 3?
Fragment shader code size 424.
C++ exit code 3. Let's It appears this exit code was returned by because it could not allocate a big amount of memory. It's annoying that this was not in any of the documentation book. Exit codes in C++. Like runs very briefly. 10 limit exceeded.
Characters. Perfect.
Let's check the comments. I will find it all. can be found in the bin folder rather than in format. For those struggling to find this, residues of pure gold. Let's see. Let me try doing control F. Arrows. Control F. Oh, stuff F. Let's see the GitHub dash. Oh, shit. There's something messing it up. This is in CPP file. Location. Missing something there. I need to add the strength. File is open. Let me just try closing and opening it again. CLion. What could be the issue? Let's see what could possibly be the issue. Let's call this. Also, didn't I change this to equation instead of DuckDuckGo? I'll check it out later. Let's rename this to shadow. Rename refactor. Shadows. Save. Yeah. Let's delete these. Recreate them. File Explorer, shadows, delete. Okay, that one made. Let's rebuild everything. Exactly. Fail to open file. Why can it not open this file? Let's see, is it based on this? Windows Surface, create service, present. Okay, this is from this area. Hmm. CSCG file, buffer data, file size, file close, return buffer. Read file. I think it's failing over here. Dot dot spv frag.spv. Fail to open file. C++. Step 30. Targeting absolute paths. Okay, let's try that. Shadows. Control H. // Control H. Also replace and files rename CLion text replace find and Control Shift R. Okay, let's try this. Check it. Let's see. Yes. Okay, it worked. Can probably make a constant string out of this. Something. Or contents or simplify this. Let's see what suggestions it can bring up. Okay, this looks much nicer. Finish define. Then you shade a path. And let's build it again. Okay, cool. Okay, glad I got this figured out.
Okay.
And it is running it from that area already. So we'll see. Can this be run dynamically? Fluid file system. Okay, let's try this. Include file system. Let's see. Whatever. Let's go into the scenic exe paths. Okay, for now let's just have a working version. Okay, cool. Let me save all this GitHub. Let's save it from here. Okay, let's see. Finish. What is the commit history? Switch to CLion. Finish tutorial. Tutorial. Button push. Okay. Changes have been saved. And it's 46. Let's go on to the next one.
Welcome back to another Vulkan tutorial. Last time we went over the graphics pipeline and created our shader programs for our vertex and fragment stages. What is left to be done is configuring the fixed function pipeline stages and creating our Vulkan graphics pipeline object. As the next step, we're going to download some code that I've written that encapsulates our Vulkan device. Stop, please.
Okay, the drawing of the triangle is still a while away.
Please don't run away just yet.
Okay.
Now, personally, I really dislike tutorials that make me download code. It completely goes against why I follow tutorials in the first place. But I think in this rare case, it might be a better way to learn Vulkan. I'm trying something different here, and can't promise it will be any better than the other Vulkan tutorials out there. But my intent is to make things more approachable by flattening out the steepness of Vulkan's learning curve. All of the code provided will eventually be examined, rewritten, or extended, so the end result is that you've gotten to the same destination learning-wise, but did so by taking a much more enjoyable route. Rather than making you slog through all of this code now, we can do so bit by bit with the context of when it makes sense to do so. Finally, my goal with this series is that it can be used as a standalone resource appropriate for newcomers, but also will work well as a next step for someone who completed the Vulkan tutorial and wants to continue learning. So if you wish to gain a line-by-line understanding. Alright, so if you're still with me, let's download the header and CPP file and put them with your other code. Follow the link in the description below to the Google Drive and download the header and implementation.
Yeah, let's go load it. Download. Down. Okay. Now let's see. Let me just check. That's been pushed. So bring in these new codes, headers and source. And CPP loop, header. Yeah. Okay.
Now drag both files you downloaded into your project and open the My Engine device header file. At the top of the file, change this to be for your window class. Update the names to match the rest of your project.
Probably window. Okay.
Place to change the My Engine to whatever you'd like. So in my case, I'm
Control F. Control Shift on. No engine.
of My Engine to LVE in both my header and implement.
Over here.
Let's update the file names as well. So first, our device CPP file name,
It doesn't have to match the place. Just to replace all. And let's rename this structure. Already. Already device. Control Shift R. Nothing new.
and then our device header file name. Then in your device implementation file, update the include at the top of the file to match what you just renamed your header.
Let's do the build. Okay.
All right, now if you scroll down to line 196, you should be getting a compiler warning that our window has no create Windows Surface member function yet.
196. Control Shift R. Engine. Refactor. Rename. Control off. Device. Replace all. The number of errors have gone away. Let's rebuild. And now this side 196. Hey, okay.
That's because it doesn't. So navigate to your window header, and just below your should close method, let's add a new public method, void create window surface.
Close, close, close. Window HPP.
which takes a VK instance and a VK surface.
Void create window surface VK instance VK surface VK charge store surface.
Go to your Windows implementation and paste it in. I'll add the class name and then in an call glfw create window surface and instance, the window, a null
LGLF create Windows surface instance and null pointer surface. Not equal to VKS success. Let's play. Another.
Now, if we go back to line 196 of our device file, we should have no more errors.
Cleared up.
Copy and paste files into your project. Sometimes your IDE doesn't add them to your build system. I've had this problem when using Xcode before, so whatever build system you are using, it's good to double check to make sure that your
Let's rebuild. It was just one else. CSRAM cost is using some of this plus cost. The reinterpret cost is quote unquote correct version. Number can be made constant, can be joined. It's fine.
Device file is actually being compiled. Now, if you build and run your code, everything should still work as it did before.
Okay, let's run it. Let's see. Okay. Still working. Nice.
Brief overview of what this device class does for us. In its constructor, the first thing we do is create a Vulkan instance. This initializes the Vulkan library and is the connection between our behavior. So when debugging, we should enable validation layers to check for errors, and then disable them for release builds when performance is critical. Next, we create our surface, which relies on GLFW, and is the connection between the window we've set up in the previous lessons and Vulkan's ability
CPP. Here's it.
to display results. Following that, we pick the physical device our application will be using. So the physical device is the graphics device in your system capable of working with the Vulkan API. This can be a discrete GPU like a 2080 Ti or an integrated GPU. In either case, we need to pick the physical device that we will be using to run our program. It's even possible to have your program use multiple devices at the same time, but this makes handling resources way more complicated and not something we'll be doing. Next, we have logical device creation, which describes what features of our physical device we want to use. And finally, it's convenient here to set up a command pool for later use. This will help us with command buffer allocation in an upcoming video. So just to reiterate, you're not supposed to understand all of this yet. For now, the only takeaways are, is one, we're setting up our connection with Vulkan and picking a physical device in our system that is capable of working with the Vulkan API. And two, we create validation layers that will help us catch errors. Now navigate to your pipeline header file and then include your device class.
Pipeline. There we go.
Next, we're going to create a struct to help us organize
Const pipeline config info and send.
ordering of your parameters doesn't matter.
Okay, we're doing device as well. Const device.
Device at the start and the config info at the end because I like how it looks better.
Right. Okay.
Parameters doesn't matter. I'm just putting the device at the start and the config info at the end because I like how it looks better.
Show context. storing this info pipeline history.
Also update your create graphics pipeline function signature to take the pipeline config in.
Take this.
Next, I'll add a private member.
Generate definition, change signature.
While storing our device reference. This could potentially be memory unsafe if our device is
VK pipeline, graphics pipeline, VK shadow. Or create shadow a steady vector code VK shadow module star shadow mode.
create the module and initialize the variable. Now, since our pipeline class is responsible for managing the lifetime of these resources, let's add a destructor with an empty implementation here just for now. And
Wait that down. The pipeline const 1 second. I'm back. Looks like I'll have to leave a bit early today after helping my mom out with some grocery shopping. I'll try and finish this up on my own afterwards, at least this part 3, and I'll continue tomorrow.